Chapter 1. The Fleet-Footed Messenger. Before Mercury was a scorched rock hurtling through space at nearly 50 kilometers per second, it was a god. The ancient Sumerians called it Nabu, after their deity of writing and wisdom. To the Greeks it was Stilbon, the gleaming one, visible only in the copper twilight before dawn or just after dusk, never straying far from the sun's overpowering light. But it was the Romans who gave us the name that stuck. They saw in this swift, elusive wanderer the perfect symbol for Mercury, messenger of the gods, patron of travellers and thieves, the only deity quick enough to dart between the mortal world and the heavens without burning. The metaphor was better than they knew. Mercury moves faster than any other planet in our solar system, completing an entire orbit in just 88 Earth days. Its surface endures temperature swings, violent enough to melt lead, then freeze carbon dioxide solid. It's been shrinking for billions of years, wrinkling like a drying fruit as its enormous iron core slowly cools. And despite being the smallest planet, smaller even than some of the moons circling Jupiter and Saturn, it holds secrets that have overturned our understanding of planetary formation itself. For most of human history, Mercury remained exactly what it appeared to be, a fleeting mystery, visible only in glimpses, guarding its truths behind the blinding glare of the sun. But in the last 50 years, we've finally caught up with the messenger, and what we've found is far stranger than any ancient myth. This is the story of the impossible planet. Chapter 2. The Solar Furnace. Stand on Mercury at high noon, and the sun fills half the sky. It blazes 11 times larger than it appears from Earth, pouring down solar radiation with an intensity 7 times greater than anything we experience. The surface beneath your feet, if you could survive long enough to feel it, would be hot enough to melt zinc. At 430 degrees Celsius, the rocks themselves begin to glow a dull red in the permanent shadows, but wait until nightfall. Without an atmosphere to trap heat, the temperature plummets across 600 degrees in the span of hours. The same ground that could vaporize lead at midday drops to minus 170 degrees Celsius by dawn, cold enough to freeze carbon dioxide into dry ice. This is the most extreme temperature range of any planet in the solar system. Not even Venus, with its runaway greenhouse effect, experiences such violent thermal swings. The reason is simple. Mercury has no blanket. Earth's atmosphere acts like insulation, holding warmth through the night. Venus's thick carbon dioxide envelope traps heat so efficiently, the planet's surface stays at 465 degrees Celsius around the clock. But Mercury's exosphere, the whisper-thin veil of atoms that passes for an atmosphere, provides no protection at all. Energy arrives with brutal intensity and departs just as quickly. This makes Mercury a laboratory unlike any other. Physicists study how solar radiation warps the fabric of space-time itself here, testing Einstein's theory of general relativity with measurements of Mercury's orbit. The planet's proximity to the Sun revealed discrepancies in Newtonian mechanics that helped confirm our modern understanding of gravity. The messenger planet, it turns out, still carries important news, this time about the fundamental laws of the universe. Chapter 3. The Shrinking World. In 1974, when Mariner 10 made the first flyby of Mercury, scientists expected to find a smaller, hotter version of the Moon, a dead world pockmarked with craters and little else. What they found instead were scars, stretching across hundreds of kilometers, rising up to 3 kilometers high, massive cliff faces cut through craters and plains alike. These weren't formed by tectonic plates grinding together like Earth's mountains. They were wrinkles. Scientists named them lobate scarps, and they told a story no one had anticipated. Mercury was shrinking. As the planet's enormous iron core slowly cools over billions of years, it contracts. And as the core shrinks, the rocky crust above has no choice but to crumple and fold, like the skin of a grape drying into a raisin. Discovery, Roops, one of the largest scarps, runs for over 650 kilometers, longer than the entire Grand Canyon. In some places, one side of ancient craters has been thrust upward, while the other side remains in place, frozen evidence of the planet's slow collapse. The math is staggering. Scientists estimate Mercury has shrunk by about 7 kilometres in radius since its formation 4.5 billion years ago. That might not sound dramatic, but it represents a loss of approximately 14 kilometres across the planet's diameter, a contraction so significant it has literally reshaped the entire surface. And here's the unsettling part. The shrinking hasn't stopped. Recent analysis of high-resolution images from the MESSENGER spacecraft revealed small, fresh scarps cutting through relatively young terrain. Mercury is still cooling, still contracting, still wrinkling under the weight of its own dying heat. The messenger planet is growing smaller, even as we're finally learning to read its message. Chapter 4. The Giant Iron Heart. Mercury shouldn't exist, at least not in its current form. When scientists finally measured the planet's density in the 1960s, they discovered something profoundly strange. Mercury is far too heavy for its size. Its density, 5.43 grams per cubic centimetre, is nearly as high as Earth's, despite being less than half Earth's diameter. The culprit is Mercury's core. While Earth's iron core takes up roughly 55% of our planet's radius, Mercury's core occupies a staggering 85%. If you could slice Mercury in half, you'd find a massive ball of iron and nickel wrapped in a relatively thin shell of rock, barely 400 kilometres thick. It's less a rocky planet with a metal centre than a giant cannonball with a stone coating. This makes no sense. Planets forming so close to the Sun should be rocky, yes, but not this metal-rich. Computer models of planetary formation can't produce a Mercury-like world through normal processes. Something catastrophic must have happened. Enter the giant impact hypothesis, or, as some call it, the hit-and-run theory. 4 billion years ago, Mercury may have been much larger, perhaps twice its current mass, with a thick, rocky mantle like the other terrestrial planets. Then a protoplanet roughly 1/6 Mercury's size slammed into it at tremendous speed. The collision didn't destroy Mercury entirely, but it vaporized and stripped away most of the lighter rocky outer layers, blasting them into space. What remained was the dense iron core, barely dressed in the remnants of its former mantle. An alternative theory suggests intense solar radiation in Mercury's infancy literally boiled away the outer rock, leaving only the heat-resistant metal heart behind. Either way, Mercury isn't just a small planet, it's a planetary skeleton, the exposed core of a world that once was. Chapter 5. The Ghost in the Machine. Mercury should be magnetically dead. Small planets cool quickly. Without internal heat to drive convection currents in their liquid cores, they can't generate magnetic fields. Mars lost its magnetism billions of years ago. The Moon never had one worth mentioning. Mercury, the smallest planet in the solar system with a surface blasted by solar radiation and a cooling iron heart, should be just as lifeless. But in 1974, as Mariner 10 swept past Mercury, its magnetometer detected something impossible, a magnetic field. It's weak, only about 1% the strength of Earth's, but it's undeniably there, and it's global. This tiny planet, which by all rights should have frozen solid eons ago, is somehow still running a dynamo in its core. Liquid iron is still churning, still generating electric currents, still producing a magnetic bubble that deflects the brutal solar wind. The question that has haunted planetary scientists ever since is simple. How? One theory suggests Mercury's core hasn't fully solidified. Perhaps a layer of liquid iron still swirls around a solid inner core, driven by the planet's slow rotation and residual heat. Another hypothesis points to the core's unusual composition. Sulfur or silicon mixed with the iron might lower the melting point enough to keep portions molten even as the planet shrinks and cools. The MESSENGER spacecraft found another clue. Mercury's magnetic field is lopsided, stronger in the northern hemisphere than the south. This asymmetry suggests the dynamo isn't centered in the planet's core, but offset toward the north, a configuration that challenges our understanding of how planetary magnetic fields work. Mercury's magnetism is faint, fragile, and by all accounts shouldn't exist. Yet there it pulses, a ghost in the machine, a heartbeat in a world that should have gone cold billions of years ago. The impossible planet refuses to die. Chapter 6. Geology of the Basin. On one side of Mercury lies a scar 1,550 kilometres across, a bullseye of concentric rings frozen in stone. The Cauldron Basin is one of the largest impact craters in the solar system, blasted into Mercury's surface roughly 3.9 billion years ago when an asteroid the size of a small country struck at cosmic velocity. The impact was apocalyptic. It fractured the crust, flooded the basin with lava, and sent shockwaves rippling through the entire planet. Mountains rose around the rim, some towering 2 kilometres high. The basin floor, once molten, cooled into ridges and troughs that reveal the violent contraction of cooling rock. But the strangest consequence of the Cauldron impact wasn't at the impact site itself. Directly opposite the basin, at the exact antipodal point on Mercury's far side, lies a region of chaotic, jumbled terrain unlike anything else on the planet. Scientists call it the weird terrain, and it looks as though the ground has been shattered and reassembled haphazardly. Hills several kilometres high jut up at odd angles. The landscape appears broken, disrupted, scrambled. The leading theory is as elegant as it is unsettling. When the Cauldron impactor struck, seismic waves radiated through Mercury's interior. These waves travelled around the planet in all directions, but they converged at one spot, the point directly opposite the impact. There the focused energy erupted upward, fracturing and deforming the crust from below, creating a mirror image of devastation on the far side of the world. One collision, two scars. Cauldron Basin is a reminder that on a world as small as Mercury, there's nowhere to hide from catastrophe. A single impact doesn't just reshape the geology of a region, it reshapes the entire planet. The messenger carries its wounds on both sides. Chapter 7. Ice in the Cauldron. In 1991, radar observations from Earth detected something absurd: bright, highly reflective patches at Mercury's north and south poles. The signature was unmistakable, the same radar reflection you'd get from ice. Ice on the hottest planet in the solar system. At first, scientists dismissed it. Mercury's equator bakes at temperatures that could melt lead. The idea of water ice surviving there seemed like claiming you'd found snowballs in a blast furnace. But the data didn't lie, and when the Messenger spacecraft arrived 2 decades later, it confirmed the impossible. Mercury's polar craters contain water ice, possibly mixed with frozen organic compounds. The secret lies in geometry and shadow. Mercury's axial tilt is nearly zero, just 0.034 degrees, the smallest of any planet. This means the sun never rises high at the poles, and deep craters near the poles contain floors that sunlight hasn't touched in billions of years. These permanently shadowed regions remain cold enough, around minus 170 degrees Celsius, to trap and preserve water ice, even while a few kilometres away, sun-blasted surfaces reach hellish temperatures. Where did the water come from? Most likely comets and asteroids that slammed into Mercury over billions of years, delivering ice that migrated toward the poles and found refuge in the darkness. Some of these deposits may be meters thick, buried under a protective layer of darker material that insulates them from the occasional stray photon. It's a paradox worthy of Mercury itself, a world defined by extremes, where fire and ice exist within walking distance of each other, separated only by the line between light and eternal shadow. Even on the solar furnace, winter never ends, if you know where to look. Chapter 8. The Exosphere. Mercury doesn't have an atmosphere. It has something stranger. Most planets hold onto their air through gravity, thick envelopes of gas molecules constantly colliding with each other, creating pressure, weather, and protection from space. Mercury's gravity is too weak, and the Sun too close for that. Any traditional atmosphere would be stripped away by solar wind in geological moments. What Mercury has instead is an exosphere, a barely there haze of atoms so sparse that particles almost never collide with each other. The air pressure at Mercury's surface is 1/quadrillionth that of Earth's. It's less an atmosphere than a cloud of individual atoms briefly liberated from the ground before falling back down, and the Sun is constantly creating it. Solar wind, a stream of charged particles exploding outward from the Sun at hundreds of kilometers per second, slams into Mercury's surface like cosmic sandblasting. The impacts kick atoms of sodium, potassium, calcium, and magnesium off the rocks and into brief ballistic arcs above the planet. Some fall back immediately, others achieve escape velocity and are blown away entirely, forming a glowing tail of sodium atoms stretching 2.5 million kilometers behind Mercury, visible from Earth with the right telescopes. The exosphere is never the same twice. It changes with Mercury's position in its elliptical orbit, swelling when closer to the Sun's fury, thinning when farther away. It shifts with solar storms and the planet's weak magnetic field. Certain atoms glow in the sunlight, creating a faint auroral shimmer around the entire world. Mercury wears its atmosphere like smoke, thin, transient, constantly being torn away and constantly renewed. The messenger planet sheds itself atom by atom, leaving a glittering trail across the void. Chapter 9. Volatiles and Volcanoes. For decades, scientists assumed Mercury's volcanic history was simple and ancient. A brief period of lava flows billions of years ago, then nothing. A dead world, geologically speaking, its fires long extinguished. MESSENGER proved them wrong. When the spacecraft entered orbit in 2011, its instruments revealed a planet far more volcanically active in its past than anyone expected. Vast volcanic plains cover roughly 40% of Mercury's surface, many of them formed more recently than the ancient impact basins. But these weren't the towering shield volcanoes of Mars or Hawaii. Mercury's volcanism was explosive, driven by gases, volatiles like sulfur, chlorine, and water vapor that shouldn't have been there in such abundance. This was the real surprise. Conventional wisdom held that Mercury, forged so close to the Sun's heat, should have been stripped of volatile elements early in its formation. Yet MESSENGER found potassium, sulfur, and sodium in concentrations similar to Earth's. The planet's surface is darker than the Moon's, likely due to carbon-rich material from the interior. Mercury wasn't the volatile, depleted ember scientists expected. It was chemically rich, complex. Then there were the hollows. Scattered across Mercury's surface, particularly in and around impact craters, are thousands of irregular, shallow depressions with bright bluish interiors. These hollows appear fresh. Some may be forming even today. The leading theory suggests they're created by sublimation, volatile materials just beneath the surface vaporizing directly into space when exposed by impacts or erosion, leaving behind these strange, luminous pits. Mercury is not a simple world baked dry by the sun. It's a planet still losing its volatiles, still exhaling into the void, still revealing that our assumptions about planetary formation were built on incomplete evidence. The messenger's chemistry rewrites the textbook. Chapter 10. To touch the Sun. Getting to Mercury is one of the hardest tricks in spaceflight. The problem isn't distance. Venus is nearly as far, and we've sent dozens of missions there. The problem is speed. Earth orbits the Sun at about 30 kilometers per second. Mercury screams along at 47 kilometers per second in the opposite direction of Earth's motion. To reach it, a spacecraft must shed an enormous amount of velocity while fighting the Sun's immense gravitational pull. Launching directly to Mercury would require more fuel than any rocket could carry. The spacecraft would arrive going so fast, it would shoot past in minutes, unable to slow down enough to enter orbit. The solution is counterintuitive. You have to take the long way around. Mariner 10, humanity's first Mercury messenger, launched in 1973 and used a gravity assist from Venus to bend its trajectory. It flew past Mercury 3 times between 1974 and 1975, mapping about 45% of the surface before its fuel ran out. The mission was a triumph, but also a tease. It could only glimpse the planet, never stay. Messenger, Mercury surface, space environment, geochemistry and ranging, launched in 2004 and didn't arrive until 2011. It executed 1 Earth flyby, 2 Venus flybys, and 3 Mercury flybys just to bleed off enough speed to enter orbit. The journey covered 7.9 billion kilometers over nearly 7 years to reach a planet that, at its closest, is only 77 million kilometers from Earth. Once there, MESSENGER revolutionized our understanding. It mapped the entire surface, discovered the ice, measured the magnetic field asymmetry, found the hollows, and confirmed the volcanic complexity. It orbited for 4 years until its fuel finally ran out, then was deliberately crashed into the surface in 2015, creating one more small crater on the planet it had come to know. Reaching Mercury demands patience, precision, and orbital gymnastics that border on the absurd, but the messenger is worth the journey. Chapter 11. BepiColombo, The New Frontier. On October 20th, 2018, a spacecraft the size of a double-decker bus lifted off from French Guiana carrying humanity's most ambitious mission to Mercury yet. BepiColombo, named after Italian mathematician Giuseppe BepiColombo, who calculated the trajectory for Mariner 10, is actually 2 spacecraft in one. The Mercury planetary orbiter, built by the European Space Agency, will study the surface and interior. The Mercury magnetospheric orbiter, built by JAXA, Japan's space agency, will investigate the magnetic field and its interaction with the solar wind. Together they'll provide the first simultaneous observations of Mercury from 2 different perspectives. Getting there requires even more elaborate gymnastics than MESSENGER's journey. BepiColombo will execute 1 Earth flyby, 2 Venus flybys, and 6 Mercury flybys before finally separating into its 2 components and entering orbit in December 2025, more than 7 years after launch. The science goals are extraordinary. BepiColombo will map Mercury's magnetic field in unprecedented detail, searching for clues about the offset dynamo in its core. It will study the exosphere's composition and dynamics in real time. Its instruments will peer beneath the surface using gravity measurements to map the structure of the giant iron core. High-resolution cameras will image the hollows and search for active geological processes. Perhaps most intriguingly, BepiColombo will test Einstein's general relativity with 5 times the precision of previous measurements, using Mercury's proximity to the Sun's warped spacetime as a laboratory for fundamental physics. As of now, BepiColombo is still en route, already having completed several flybys and sent back tantalizing preview images. The full mission won't begin until late 2025, but when it does, we'll see Mercury as never before, through 4 eyes instead of 2. The messenger is about to speak in stereo. Chapter 12. The Future of the First World. Could humans ever set foot on Mercury? The question sounds absurd. The temperature swings would kill you. The solar radiation would cook you. There's no atmosphere to breathe, no water to drink. Except for ice locked in polar craters, you'd need specialized equipment to reach. Mercury seems designed to repel human presence. And yet, engineers and futurists have begun sketching scenarios. The key lies in Mercury's rotation, or rather its peculiar lack of speed. The planet rotates so slowly that its day lasts 176 Earth days. This creates narrow twilight zones near the poles where temperatures hover in a relatively moderate range, neither blistering nor freezing. A mobile base could theoretically stay in perpetual twilight, creeping along the terminator line between eternal day and night. The solar energy is staggering. Mercury receives more than 10 times the solar flux that Earth does. A solar farm on Mercury could generate power with unprecedented efficiency, energy that could fuel industrial processes impossible anywhere else. Some theorists propose mining the planet's metal-rich surface, extracting iron, nickel, and rare elements to build infrastructure in space without launching it from Earth's deep gravity well. The ice deposits offer another lifeline. Water could be extracted, split into hydrogen and oxygen for fuel and breathing. Permanently shadowed craters could house habitats shielded from radiation. But here's the truth. Mercury won't be colonized soon, if ever. The engineering challenges dwarf anything we've attempted. Mars is closer, easier to reach, more forgiving. The Moon offers similar resources with far less risk. Mercury remains what it has always been, extreme, uncompromising, at the edge of what's possible. Still, we've visited the messenger now. We've learned to read its language, and humans have a habit of going to impossible places, simply because they're there. The first world may yet see footprints in its ancient dust.